Right. Welcome everyone to our very first Science Social hosted by our iMotions Berlin office. Join for a second, Marcus.
Oh, sure.
We have Marcus here as well. We are a part of the iMotions Berlin team. Happy to host our very first Science Social with Hagen from audEERING. If you know of our voice analysis module or have heard of it before, you know that this is a really nice way to look at expressed emotion, particularly in qualitative research or research where there are think aloud tasks, focus groups, interviews, and so on. It gives you a really nice way to look at emotion in speech. That is language independent because it looks at prosody measures. So you get things like fundamental frequency, loudness, pitch, intonation, and so on. But more importantly, from just the voice and how people speak, we get the dimensions of emotion. So you can look at the emotional dimensional model and look at valence, arousal, dominance as emotions on which or as dimensions on which emotions are measured, or categories such as angry, happy, sad, neutral, that fall in the categories between the different dimensions. Individually, each model gives you a lot of information. Together, combined, they also give you a lot of different insights based on how people are speaking. Because it is language independent, it translates nicely all over the world. And this is what Hagen's going to be presenting today. So Hagen is a senior researcher at audEERING, has worked extensively on the emotional models that we integrate also within iMotions. And so yeah, send us all your questions. Feel free to ask us anything you would like, and we will also make sure to pass them on to audEERING and to Hagen. Hope you enjoyed this talk. Yeah, and look forward to hearing from you, and we'll talk again after the talk. Thanks, Hagen.
Yeah. Thanks for the introduction, and I will switch to my talk. And first I wanted to mention that all the work I'm presenting here was basically a collaboration with a colleague from mine, which is Anna. She's also one of the first authors of one of the papers that are dealing with this topic. And yeah, I think I will also first start a little bit with an introduction to emotional expression, because it's still a little bit complicated. I mean, the obvious thing is that it's a key component for communication, because I mean it's not only the text you are saying, but also how you say it. And then when we are talking about emotions, we usually or measure emotions. There are two different ways of doing it. And in the figure we saw before, we talked about emotional dimensions and categories. And the dimensions I'm picking up here again, but usually I use the term attributes for them to be to try to be a little bit more correct, because there is not an exactly one-to-one match, so you cannot say if you have the dimension measured that you can directly or that you can always map to an emotional category. It works in a lot of cases, but it's not that it's a mathematical mapping, so to say. Then also for the attributes, you will see that in some literature people from time to time leave out dominance and just focus on arousal and valence, and it can also happen that for certain measurements you will have a high correlation between dominance and arousal. But in general, if we talk about the emotional attributes, it would include arousal, valence, and dominance. Then of course emotions can also be measured or expressed in other modalities. But we are focusing on a voice, and in literature you usually find what we are doing under the term speech emotion recognition. So that's the reason why I wanted to mention it here as well. So let's start with the attributes, because I mean maybe not everyone is used to the naming. If we have the attribute arousal, it basically says if when you are speaking, if you are more passive or active, or also from time to time people say how aroused you sound. Then for valence, it's more a negative or positive sound, and dominance usually refers to the control that a speaker might have in a conversation. Then those attributes most of the time emerge from the physiological state of your body. So basically the body has a way to measure its current state, also in response to the environment around it, and some of the responses then lead, for example, that if the body recognizes that you are in danger, then usually this leads to some kind of arousal and stuff like this. But it's not that those attributes are only related or can lead to emotional categories, which I will talk about in a minute, but they might also be part of other things, like, or play a role in other things like beliefs and memories and perceptions. This is also why I said that I do not always have a one-to-one match and call them attributes and not dimensions. So for categories, I have listed here happiness, sadness, and anger, which are also the main ones that usually we work with. But in principle, the list can go on and on and on, and it's for some terms is also in the literature not completely clear what is an emotional category and which not. But usually with happiness, sadness, and anger, these are very well defined ones. One point which makes measurement a little bit complicated is that within a category of emotion you have high variability of physical and mental features that lead to that emotion. And what is slightly different, or what is more pronounced here compared to emotional attributes, is that the emotion also depends very much on the situation and also the cultural context. This is also one of the reasons why you need to look and check that your predictions are really language independent, and maybe there are situations where this might not be the case. And then, because I have said now several times that there is not a strict mapping between attributes and categories, I just wanted to present one counterexample. So it might be that you experience fear, but you still have a positive valence, which is in most of the cases is not the case, but for example, if you're on a roller coaster, this might be the case. And another challenge we have with emotional categories is if we do experiments with humans, then also humans will not always agree on the expressed emotions. That means usually if we do experiments with human annotators, we need to have more than one annotator, so we can be sure in the end that we have the label we are looking for. And also to see if the example, for example, if all raters agree, or if we have an example where maybe all disagree, and we should have to see what we can do with this kind of data or not. Then let's start with machine learning. So if you want to recognize emotional expression, the usual way is that we need some labeled speech data where you have audio examples, those that have a label for an emotion, and the data can be acted. For example, for emotional categories there are a lot of acted data sets, but it can also be natural conversations. So you start with a recording of a podcast or a YouTube video or whatever, and then present it to annotators in order to get labels for different parts of the recording. Then a few years ago, as with most of the machine learning research and speech, we get a big jump in performance when we switch to use transformer models, which are not only in speech, but which have in general very high or useful applications at the moment. And what is from time to time also a little bit challenges with emotional recognition is that your accuracy of the models, if you measure them, it depends a lot on the data set you use, which kind of range you achieve. So for example, if you have a small active data set, you can have accuracies that are over 90% if you use samples. So if you split the data set and train and test, for example, and use in-domain test. But if you have natural conversations and you have and the data was not part of the training set, it might be that accuracies are only in the range of 60 to 70%. Which also does not automatically mean that the models do not reach human performance, because if you compare a single human against the average labels you have from all the humans, you can also get accuracy that are around 70% as the data is changing. Yeah, but the focus of our work and what I would like to present here is to not focus on accuracy, but look for other measurements. And there are several reasons for it. So first, you might realize that if you have models that have the same accuracy, it does still not define how the models behave in practice, because they can make the errors at different places and which can lead to very different behavior if you want to integrate it in an application. Then, due to the underspecification of machine learning problems, models usually always learn a few shortcuts, which also means it's a good idea you try to find those and try to eliminate those. And basically what we are most of the time doing, so we want to try to quantify the behavior of a model and measure how robust a model is and is there potential for bias. And on those three topics I will pick up later and show examples. And how. So the best way, or one way you can try to work and have a software framework in order to evaluate your model is to do tests, like you also do for software. For machine learning, there's also the area of testing. That's a little bit more complicated, because usually it's harder to define if a test fails or not, so you have to define some thresholds, and in most cases those cannot be defined automatically, and for most of the tests you cannot say it has to be 100% correct in order that the test passes. And you also have the problem that a lot of the data might not come with a label, or if you change existing data, the question is how much am I allowed to change it without changing the label. So for example, if I have audio example with a set emotion and I add laughing kids in the background, then at some point I would expect that the sample is no longer labeled as set, but maybe as heavy or as both or whatever. So there you need to be a little bit careful. So first I wanted to start with correctness tests. These are the most straightforward, because they are related to accuracy and they are also included there. So we measure accuracy along different dimensions. So we look at recall and precision, and also precision per class, and all those stuff you can do. And for emotions, it's also interesting. I talked a lot about that there is not always perfect match or mapping from attributes to categories, but there is data where you have these, can do this mapping, and where you also might have labels for both, and where the model should be consistent. So if the model predicts arousal and valence and dominance, and it predicts also anger, then the three values of arousal, valence and dominance should map the predicted emotional category. So these are things that I would call consistency tests for emotional recognition models. Then another thing we look for is that the distribution of the predicted values are matching the distribution of the ground truth values. So for example, that the range of the values matches. And then another thing which might be important, it depends on the application, is that the accuracy is also very similar on a per speaker level, so that it's not working for one speaker very well and for another one it does not work at all, or stuff like this. For test thresholds, there are basically two ways to define them. So one is if you have annotated data, you might look how a human performs on all these possible tests, and say I will pick the human performance as my test threshold. Or if you have an application that requires better accuracy on some levels, then of course you can also request a higher test threshold. For robustness tests, it's basically that you are not doing a machine learning model for university and conferences, but it should be work in the real world, which means if you switch the microphone, if you have different rooms, if you have background noise, the model should still predict the same value, more or less. Here, test thresholds is a little bit more complicated. At least so far we did not found an automatic way to set those, but we think about how robust the model should be in order to be okay. So this is, let's say, the hard part here to come up with good test thresholds. Here a few examples. So for example, for testing robustness against background noise, you can use other recordings and add them to the signal. So for example, we have a clean speech signal. In this case, it's a German sentence.
In Stunden wird es soweit sein.
And then you can add different background noise. So for example, bubble noise means we have different speakers in the background.
In Stunden wird es soweit sein.
It's not too loud, so that we are be sure that the emotion that is present in the sample is not altered. Or, which is also interesting, if you have a noise that is not constant, but only in parts of the signal, like sneezing.
In Stunden wird es soweit sein.
Then it would also be great if this has not a big influence on the result. I mean, here is not the real test. These are just some example outputs of the model you would get for arousal, valence, and the predicted category. And you see in these cases it does not change too much, but we will see later real results for it. Another one which is not so easy to test is different microphones. One way is if you have dry speech recordings, you can also use impulse responses from different microphones and convolve them with them. But we also have a test speech database which was recorded simultaneously with different microphones. So this is quite nice because the goal should also be that the predictions of the model should be more or less the same, because the speech is not altered, it was the same speech, just with different microphones. the one with the headset.
There were barrels of wine in the huge cellar.
And if you use a boundary microphone, then the speaker sounds a little bit far away.
There were barrels of wine in the huge cellar.
Yeah, and here you see that things that might happen. So if it drops a little bit in loudness, the recording, you might see a slight drop in arousal. But in general, the model should not drop too much. This would be the requirement. So continue with fairness tests. So here the goal is to measure if the model shows a bias against any kind of speaker attributes. Speaker attributes might be gender, accent, or language. By the way, I should have said I present not all the tests we're doing here. I just pick always a few examples that I think are the most interesting one and also easy to understand. But you can also add slightly more speaker attributes. Here the good thing is that you can determine the test thresholds automatically, because the idea is if you have a model that predicts random values, it should not have a bias. And then your threshold just depends on how many samples your data set has. I mean, if you have only 2 samples, then of course it's not so easy to measure if a random model has a bias or not. But if you have a lot of data points, then you know what kind of thresholds you can select. Here is one example. I mean, one problem with the testing fairness is that in an ideal case, you have lots of data sets that have labels for your prediction tasks. So for example, you have emotion labels, and then you have also labels for gender or language, and then you can measure that your accuracy is the same across gender or different languages or so on. But one of the challenges, especially for language, is that you have not always data or large data sets with labeled. So this is why we also came up with a few tests that can use data without emotional labels. So for example, if you have, I think Common Voice from Mozilla is a good example. There you have, these are recordings from audiobooks, and they are available for lots of different languages and usually contain a larger number of samples. And there the idea is that if you predict with a model on all these samples, that the distributions of the output of the model, which you can see here. So in blue we have a prediction of valence. On the x-axis we have the value, the valence value going from 0 to 1. And the blue one is basically the distribution of the model predictions over all languages that were included in the test. I think here it have been 6 or 8 different languages, this example. And then the red one is if you do the prediction only on the German samples. And the test would then be, you have to come up with a measure that measures how similar distributions are, and then you can define if they are the same or not. So now the interesting part, if you have set up all those tests, I basically here on the x-axis have written down all the tests we talked about before. So we had 4 correctness tests looking at consistency, distribution, accuracy for regressions, then speaker average values, and then 3 fairness tests for accent, language, and gender. And we have 3 robustness measures for background noise, microphone, and room. And on the y-axis, you see now the percentage of all the tests that have passed. Because I mean, if I say this on the x-axis, I define a test of correctness consistency, this might still include a lot of different tests because you can look at different data sets and so on. And on the y-axis, we have then the overall number of past tests for this. So then in blue, you see results of a model that we published a few years ago as open source. This model was, so and you also look only at results for valence in this figure. And the open source model was trained on English data, so MSP podcast data set. And the red one is the production model that is currently integrated with iMotions. And when we started developing it, we first looked at basically the test we had with the open source model to identify areas where we need to improve. And not so surprisingly, the open source model has problems with robustness because I mean, if you do not account for it during training, you usually always have problems with robustness because and if you have small data sets you are training on, then they are not diverse enough in order to result in robust models. Correctness can also be still improved, and we saw that for fairness language it was not perfect, which is maybe also not so surprising if you only train on English, the open source model. So we started to tackle those different things. One problem is that when you do it, it can have consequences that go from one test to the other. So for example, if you prove robustness, it might be that correctness goes down. So this is a little bit of the hard part of this, that you try to optimize all the tests together. Before going into more detail what exactly we did or how we did it, maybe I first switch I will first say a little bit. So for robustness, the usual stuff you are doing is you do data augmentations, so you can add background noise and also try to simulate different microphones and other stuff during training. Then for fairness language, the most obvious solution was to add more languages to the training. I mean, it's not so hard if you only have English before. And for correctness, we first tried to force the model a little bit more to align the attributes and categories better. This is why you see an increase here with consistency, but the overall performance was still very similar to the open source model. We basically continued this. I mean, the model I wrote here production, which usually means the model is already a little bit older, and in the meantime we have another one that is currently, I think, integrated on our side and is then also available for others. Yeah, and there you see that we continued with the approach, and now we finally managed to get the fairness language tests in an area that looks better. Robustness is, compared to the open source model, also a big improvement, but it's still hard to get it to 100%. It's not a trivial problem. And with correctness, I think I think it's very nice that the consistency is now again better. I mean, as I said, it's not that you can always do the mapping, but if you have data sets or have you examples where there should be a clear mapping between whatever that valence and arousal are high and it's a happy example, and the model says it's neutral and it has high and valence and high arousal, and this should clearly not happen. And this is one of the things that we try to improve here. Yeah, for language, I wanted to go a little bit more into details what we did and what is still challenging. I mean, just a reminder that the main tests we are doing here or did before was based on unlabeled data. I mean, this has the advantage that you can expand it easily to more languages, but you might still be interested what is going on with labeled data. So that for that reason we also spent a little bit of time, and especially for the emotional categories we were able to extend the tests to labeled data for 10 different languages. You will see the languages later in the results. We also tried to get a mixture that is culturally more diverse, so it's not only European languages, so to say. And then for training we also tried the obvious thing, integrating more languages into training. For testing, it's still a little bit the challenge that some of the data sets that you can find or label yourself are on acted data or on natural data. And this means if you have for one language only acted data and for another one only natural data, and you see that the accuracy for one language is higher as for the other, it's not so easy to say what is the influence of acted versus natural and what is the influence of the performance on the language. So that means in an ideal case we would be able to try to balance more the natural and acted recordings, but this is still, it's an ongoing challenge because it's also expensive to label data yourself. So here is an example output. If we look at the evaluation on the 10 different languages for emotional categories. So on the x-axis you see the languages. We have Bengali, German, English, Spanish, French, Italian, Kannada, which is from southern part of India, Quechuan, or however you pronounce it, it's in the India region, so Peru for example. Lama is a word that comes originally from that language. Then we have Thai and Chinese. It's an over category. It can be different Chinese languages. The problem is that for some of the data that is collected, it's not completely clear. I mean, usually it's just labeled as Chinese, but it's not clear if it means it contains really different kind of Chinese languages or just one, and you have to figure out which one. But if you have, there we can maybe also improve and see if we can classify this a little bit more. So, but I mean, this is now the results for the current production model, which was trained on English, German and Chinese on acted and natural data. And there you see that you also for other languages you get an accuracy that is at least in a similar range. I mean, you also always have the problem that accuracy for different speech emotion data sets can vary, but at least it looked already more promising than we might have expected, because cultural effects can be there for emotion and you don't know exactly exactly how it works. We then further extended languages. So now we also have Bengali, French, Italian, Portuguese in the training data. And here you see one effect in the evaluation, which is also a little bit unfortunate. So before, all the evaluation was done on out-of-domain data. So none of these data sets we used for evaluation was included in the training. And now for Bengali, French and Italian, we also included the training parts of the data sets into our training, and then you automatically get a boost for the languages here. But the problem is, or why we did it, is because in those languages we still have too little data in order to say we can afford to not use it during training and just for testing. But this again makes it then a little bit harder to interpret the results with the data. Good. Then after a little bit of going deeper for how we worked on improving language, fairness for different languages, I would like to summarize. So I introduced emotional attributes, which are arousal, valence, and dominance, and are usually measured or are measured by our models as the regression models and return values between 0 and 1. Then we have emotional categories where we focus on happiness, sadness, anger, and also neutral is always a category that we return. Then I introduced why you should maybe test the models and what you should measure, especially correctness, robustness, and fairness, and that you can use the tests to support your model development and also in order to report results for different stakeholders, because I think some of those are much more interesting than just having a single accuracy number. And so far our research seems to indicate that speech emotional recognition can generalize across languages, which is for the emotional categories, because those are more influenced by cultural backgrounds. Not completely obvious that this might be the case, but at the moment it looks promising. Okay, thank you. Questions? Should I read them to me?
All right. Stand closer to the mic. All right. Thank you, Hagen. Thank you, everyone. Maybe we open it up to the audience here first, and then we can take the online questions as well that I've made a note of. Any questions from the audience here?
Actually, yes. When you test languages, the amount of countries that, or languages that you choose, is that a global representation, or is there still like more to be added to it?
Yeah, I mean, I'm pretty sure there's more to be added to. I mean, there are thousands of different languages, and we also did not follow a systematic approach. I mean, you can try to classify languages and then see that you have tests for every possible group of these classifications. But at the moment, I think the tests are more driven about for which languages data is available.
Okay. And
or enough data is available.
And in those languages, how do you account for gender? Is there any difference between genders in a given language?
I would, at the moment we account mostly for it by just the that we use high number of samples. I mean, that's right. I'm pretty sure if you look at something like Common Voice, it's more likely that there are males that do recordings, I guess, compared to females. But it's a good point. I mean, the good thing with gender is that you can use other models in order to provide gender labels if they are not in the data. And then you can also try to do it. I mean, our focus was not so much on gender because the fairness tests for gender we had so far, they were always very good. So there was not, we were not expecting that our speech emotion recognition model was behaving differently due to different gender.
And maybe add on to that, that was also my last question with the whole catch-22 of what languages have data sets available that you can annotate or not. Do you have a more philosophical question overarching for the entire community working on this? What would be your request to everyone? Like, how would you look for data sets and what would be good?
Yeah, I mean the biggest challenge is not that there is not data available for different languages, but one of the biggest challenges with the unlabeled data is that mostly, or if it's audiobook recordings or other things, then they usually reflect not all the possible values of emotions. I mean, you can see it here already. It might be a little bit squashed due to the model, but usually you are missing data points at the very low and very high end. Yeah. And this is was also one of the reasons why we started into looking to also get tests with labeled data, so to make sure that that we also test for emotions that might be not part of those data sets. So the biggest challenge for annotating data is that basically you have to pre-filter them, because if you just start annotating and then in the end you filter the data based on annotations, this means you would need to annotate 1 million samples to have 100 in the end that are balanced. Yeah. So this means it's if you have already a model that is good enough that can do the pre-filtering, then it's working out to doing annotations yourself. But otherwise it's a very challenging job, so you cannot simply start annotate and hope at some point there will be enough sadness or whatever.
We need more sadness.
Yeah.
Talking about annotation, some of the questions were also around how you handle reliability of different raters. You said there are multiple raters annotating. So, like, is that how you correct for it? Are there anything to assure reliability?
Yeah, we basically have two things. So we have our own pool of annotators. They are trained and also screened in order to be reliable, but of course they are limited mostly to native German or English speaking persons, which might not be ideal to annotate other data sets. What we have started is to use also cloud-based annotations, and there we integrate a screening session before. So you have first to annotate something, and then if you're good enough you can continue, and if not, then not.
And then if they continue, do you also sample throughout to make sure that everything is like all the annotations or all the annotators are coherently annotating the same kind of data?
This is, I'm not sure if you're talking about the same, but this is something that is a little bit challenging. So for example, also for our own annotations, let's say we have a data set and we require 5 annotations per label, but we have 20 or 30 annotators,
Yeah.
then we do not just pick 5 of them and let them annotate the whole data set, but we basically say they can all annotate the data set, and the first 5 that annotate one sample are then annotated that sample. That makes it a little bit more complicated to do certain analysis. That would be easier if always the same annotator would annotate all the samples, but it's also very hard, especially if some are then on holiday and you have to wait until they're back or stuff like this.
But this is also good because you talked about the heterogeneity of the human population, and every annotator will be different, so it's good that you mix and match so you get the heterogeneity in the training data set as well, right?
Yeah.
That makes sense.
I've got a question regarding the transition from neutral to target emotions, because of course we have been integrating facial expressions the last couple of years already, and a lot of our customers were using face morphs as stimuli in order to show it to participants, and also to actually analyze facial expressions in terms of the change of faces from a neutral kind of status into a target emotion. And here the facial expression engines are generally generating some mixed results. For example, happiness, but then the person is actually being classified as being very sad. And I was wondering if you see the same in terms of moment-to-moment transitions, that actually makes it harder for a machine to detect the target emotion in a sentence, which is quite obvious for us as a human coder. Do you see these tendencies as well?
Yeah, I think there might be 2 parts to it. So first, I mean, especially for facial expression, I think they are even more context dependent than audio. So, I mean, if you have a face that is screaming, it might be happy, but it might be fear. So it's very subtle if you just see one image. And then the other part is, if you just train a model to classify categories, you miss a little bit on the transition parts, because it might be that some happiness is more happiness than another sample, which might be more neutral. In our case, I think we are covering this a little bit because we are training one model that also has to predict arousal and valence, which are actual aggression problems. So there you have a continuous value. And for example, if you then have 3 different or 2 different happiness examples, the model can see that maybe there are different arousal or valence values that are related to this, and can use those in order to learn that this is maybe more too neutral or not. So this is where we spend some time in order to optimize this, and which resulted in getting a little bit of boost for the consistency.
Okay.
Because it was indeed very challenging if you just train on emotional categories.
You didn't speak a lot about how good the fairness models are here, like the fairness tests are here. Can you say a little bit about why the fairness tests are so good, and we just discussed why the other 2 are not and how to improve it, but what makes fairness better?
I mean, why we have from the beginning on good fairness for gender, I don't know, but maybe the features for emotions are simply not that different for female or male, or if they are, then the model does not learn any bias from it. I mean, of course, during the training we looked that the data is balanced, and maybe the MSP podcast data was also balanced enough, because I mean for the open source model we just use the standard MSP podcast training set and did not any balancing of the data. But I mean this is, for example, one approach you can do if you see that you have a balance, that you have a bias, that you look at your data, maybe the one attribute where you have problems with is underrepresented, and you have to make sure that it's not the case in the data. And I mean, in principle, this is also how we try to improve language. I would say we are not at a point where we can balance languages, because the amount of English is still very high, but you can at least start adding more and more other languages.
Right. I think we've covered a lot of these. You spoke a little bit also on this slide on the robustness correctness trade-off. Could you say a little more about that?
Yeah. So the thing that can happen immediately is you see you have robustness problems with background noise. Then your first idea might be okay, then just add augmentation during training. So use the clean audio and put different kind of background noise to it, and then train the model again. And then what can happen, or happened at us very often to us, is if you then look at your accuracy measure, whatever it is for your task, then you see that it usually slightly drops.
Okay.
So if you only add augmentation and do nothing else, then it, at least for speech emotion recognition, it usually does not also improve the correctness, but most of the time it's the other way around. But it's also because all the data sets you use to measure accuracy, they have no noise. I mean, it's not a good representation of what you have in reality. And if you add then also noise to them, then I guess your new model is then better than the old one, because the accuracy for the old one would simply drop.
Of course. Yeah.
So,
Right. I think we've covered all the questions here. Thank you everyone for joining. Thank you everyone who came here in person. And yeah, hope to see you at the next event. Thank you. And thank you, Hagen.
Yeah, thank you.